Hello students, welcome to our first lecture on module 2 where we will discuss some of the physical principles that will govern various hydrological processes. Throughout this course we are going to talk about a few hydrological processes time and again, and we will go in depth of all these concepts, which would include precipitation, evaporation combined with transpiration, called together as evapotranspiration. Then we will also talk about some surface flows and subsurface flow. Anything that is flowing beneath the surface would be subsurface, and anything that is flowing over the surface would be classified as overland flow. Now, one thing is for sure that when we talk about hydrology, we are essentially going to deal with fluid, which luckily for us is water. And not only that, this is fluid in motion. And whenever we talk about fluid in motion, the best tools that are available to us, we can borrow them from the fluid mechanics. And first choice comes to be Reynold transportation theorem, which is extensively used to study fluids in motion. Now, from your course in fluid mechanics, you must remember the derivation and genesis of this Reynolds transportation theorem, why it is used and how to derive it for various scenarios. But given its universality and applicability in various processes of hydrology, we will quickly do a quick refresher around Reynolds transportation theorem and try to understand its derivation. Now, one thing is that we have to keep in mind that whenever we are talking about Reynolds transportation theorem, we are essentially using the Eulerian view. And what we do in Eulerian view, we go with the concept of control volume, which will be a three-dimensional entity in the case of fluids, which will serve as our reference volume and with respect to which we will make all the studies. Then we will also talk about the concept of system, and we will consider the fluid packet as a system that is moving, and we will try to apply various conservation principles on that system. We will also deal with two kinds of properties here. One is extensive properties represented by B, and another would be intensive properties, which are mass independent. So when we talk about extensive property, for example, momentum is mass times volume. So we can say that momentum is an extensive property. Measure of energy. You know that total energy is given by kinetic energy plus potential energy plus internal energy. Now, internal energy is also directly proportional to mass of the body under consideration, and hence energy is also a extensive property and represented by B. Now, when we take the differentiation of B with respect to mass, we end up with a small representative quantity called as beta, which is dB by dm. Now, in case of mass itself is an extensive property because it depends on mass of the body. So beta for mass would be 1, beta for momentum would be equal to V, and beta for energy would be equal to V square by 2 plus GH plus small eu, where eu represents an internal energy per unit mass. Now, why we are talking it in the context of hydrology? Because when we'll talk about precipitation, we are essentially talking about movement of mass, which in this case is water vapors. When we are talking about evaporation, we are talking about interaction between energy and mass. That is, sunlight will fall on water, it will give it enough energy for excitation. That is, that phase change will happen from liquid to water, or from ice to liquid and liquid to water. And we want to understand and quantify how much water would be transformed from one form to another, as we want to understand the hydrological cycle that is phasing, or that is giving shape to the various water processes happening on our Earth system. And that's why we are interested to explore these principles. So let us take a very simplistic view. That is, we consider a control volume represented in red color and a system represented in green color. At time t equal to t naught, we assume that the boundary of control volume and system, they coincide with each other. However, this system or the fluid that we are looking into, that is in motion, and at t plus delta t, it will occupy a new position represented by t naught plus delta t, as our initial time was t equal to T naught, and we are interested to understand how the extensive properties of the system has changed with respect to time t, and to do that we will use Reynolds transportation theorem. Now, We know that system initially was at stage comprising of 1 plus 2, and 1 plus 2 is also is equivalent to our control volume, and at t plus delta t our system has moved to 2 plus 3. So if we can study what was the amount of extensive property at time t plus delta t, which can be measured by looking at extensive property contained in 2 and extensive property contained in 3, because this is our entire system that is under consideration, at t plus delta t minus what was the state of the system at t equal to t naught, which is given by b1 plus b2 at t upon delta t. Solving this equation should tell us how much is the extensive property within system has changed. Also, we will consider an infinitesimally small element of volume dV, and let us say that the density of fluid under consideration is rho. We know that mass of this system can be calculated by multiplying density by volume, so it would be rho dV. If we multiply the extensive property, or the differentiation of extensive property, which we said beta, by which is the extensive property per unit mass, by the total mass, we can calculate what is the small amount of dB contained into this infinitesimally small volume. Similarly, similarly, if we consider an element here which has a cross-sectional area A, or let us make it dA, and fluid is flowing with the velocity v, and there is some angle between the normal to area and v, we can always resolve the components using vdA. Now, if we are interested in looking at rate of change, small dq, that what is the flow rate through this small funnel under consideration, where q is always in meter cube per second, so it has to have per unit time. What we will do, we will again do the same thing, that volume when multiplied by density should give us the mass contained, and if we multiply it by beta, it should give us the extensive property contained in this small element. Now, when we talk about rate of flow of extensive property, we are essentially looking at the per unit time. And volume, as we know, is given by dA multiplied by delta L, where delta L is the length of this small unit that we are considering, multiplied by rho multiplied by beta delta T. And this delta L upon delta T, in fact, is the volume of fluid under consideration, and that should be in the direction along the area that we are considering. So we can write this as rho beta V dot dA. Now, when both A and dA, they are in same direction, this particular product can be easily computed, because if this is our dA, this is our V, we simply know that the dot product is V dA cos theta, and our answer should be straightforward. On the other hand, if we consider this segment 1, where we draw a similar pipe or the small element of length del L, the velocity is in this direction because our system is moving here. Our area vector is in outward direction, because by convention area vector is always taken away from the control volume. So our area vector is somewhere here. So the angle between velocity and area vector, it is given out to be cos theta. And if we have to calculate the dot product in this case, where if this is dA, this is V, we have to look into the angle which would be given by 180 degree minus theta, and we know that cos of 180 minus theta is equal to minus cos theta, and hence for elements that are on left side of our control volume, we can write this expression as rho beta V dA with minus sign. Now, since we are talking about this infinitesimally small element, if we are interested to understand how much flow has taken place through the cross section, what we will do, we will take the double integral across the surface. We will take the double integral across the surface. Here, if we are interested to know that what is the mass contained in the volume, we will take the triple integral over the control volume, and now we will put these expressions together and try to see that how it relates to dB system by dt. So when we talk about 2 plus 3, you can clearly see that this 2 is actually nothing but it is BCV minus B1. So we can write dB upon dt of system as BCV minus B1 plus B3 at t plus delta t minus what is happening at time equal to t is 1 plus 2, which in fact is our BCV at time t divided by delta t. We can write this expression as del B sys upon del t equal to BCV at t plus delta t minus BCV, let me write it again, BCV t plus delta t minus BCV at time t, plus we will also collect these other two terms which include B3 t plus delta t minus B1 t plus delta t, and this whole is divided by del t. Now if we focus on the term that I am highlighting in green, it is nothing but it is change in extensive properties in control volume with respect to time, and other two terms, they represent the flux, that what is the rate at which material is flowing in control volume A, because that is talking about B3 t plus delta t upon delta t minus B1 t plus delta t upon delta t. So basically what is the rate of flow from surface 3 and surface 1. Now what we did last time is basically we try to look into the expressions of B3 t plus delta t and B1 t plus delta t with respect to time when we are talking about the flow through the surfaces. Because if we look at surface 1 and surface 3, how much change is happening in surface 1 and 3 is basically what is the rate of change of inflow and outflow of the extensive property under consideration through the boundaries or the surface of the confined control volume. So we can write that in case of 3, since the normal vector to area and velocity, they are aligned with each other, this expression can be written as integral over control surface beta rho v times dA, where dA is the area of that small tube that we were considering. Similarly, here we considered that in case of 1, wherever we have entering surface, the angle between flow and area vector, it is greater than 90 degree. Hence, we have to take cos of 180 minus theta, making this term positive, and we will say that if this is cross surface 3, this is control surface 1, and beta rho VDA again can be written here. And we can combine these two expressions here and say that del B system with respect to time is rate of change of BCV with respect to time, and integral over the volume of mass contained in this control volume, which is beta rho dV plus flow through control surface beta rho VDA, and this in turn is equal to rate of change of extensive property happening in system with respect to time. And this relationship is famously known as Reynolds transportation theorem. And we will use this Reynolds transportation theorem as it is when we will go towards estimation of evaporation rates and evapotranspiration rates, as well as when we are going to study certain concepts of formation of precipitation, specifically the convective thunderstorm cells. So again, If you are not clear with this, take a quick look at the discussions and also refer to your fluid mechanics book, because this Reynolds transportation theorem is going to be our backbone as we proceed with the analysis. Now we will apply this Reynolds transportation theorem to conservation of mass, and we will derive continuity equation, which is another fundamental equation that is used time and again in hydrology, which we will discuss in our next lecture. Thank you.